Hello everyone, this is Professor Roman. Let's continue the group theory lectures. We're moving on to chapter 7 now, and it's time that we increased our catalog of known groups, as well as take a more careful look at the dihedral groups that we've already discussed rather peripherally. But first, I want to look more closely at cyclic groups. Cyclic groups are not only the simplest types of groups, but they're also the building blocks for many other groups, such as the finite abelian groups, as we will discuss later in the course. In addition to that, every element of any group generates a cyclic subgroup of that group, and so cyclic subgroups are ubiquitous throughout group theory. I'm going to leave it as an exercise to verify that every group of prime order is cyclic. I think I mentioned that in an earlier lecture. What I want to do now is take a look at the subgroup lattice of a cyclic group G. The subgroup lattice is a complete lattice under set inclusion where meet is intersection. Also, in the subgroup lattice, frankly of any group, not just a cyclic group, the set inclusion relation is the same as the subgroup relation. And that's to say, if you have two subgroups of G, say column A and B, then A is contained in B if and only if A is a subgroup of B. So we can feel free to use either relation more or less interchangeably. The theorem in the previous chapter, Theorem 6.6, told us that every subgroup of a cyclic group G, let's say generated by the element A, is cyclic, and so it will have the form subgroup generated by a to the k, where k is a non-negative integer. The subtlety in understanding the subgroup lattice comes in determining whether or not all of these subgroups, the ones generated by powers of A, are distinct or not. And for this purpose, we are going to have to separate the finite and infinite cases. This is something we did before when we talked about generators of a cyclic group, also when we talked about homomorphisms from a cyclic group to another group. So let's look at the infinite case first, because that is the simpler of the two cases. So suppose that G is generated by an element A and G has infinite order. Then it turns out that for each integer k bigger than or equal to 0, we get a distinct subgroup generated by a to the k. And then this will account for all subgroups of G. So it is the subgroup lattice. And I'm going to leave proof that these subgroups are distinct for distinct values of k as an exercise. As to the order relation in the subgroup lattice, we have for two non-negative integers k and j, the subgroup generated by a to the j is contained in the subgroup generated by a to the k, if and only if the generator of the contained group, a to the j, belongs to the containing group. And that's equivalent to saying that a to the j is a power of a to the k, say a to the ik for some integer I. But because a has infinite order, this will hold if and only if the exponents are the same. And this is equivalent to saying that k divides j. And here, because it's possible that j and k are both 0, we have to assume or declare that 0 does divide 0, just for this purpose. So in summary then, and again, because the inclusion relation is the same as the subgroup relation, we can write the group generated by a to the j is a subgroup of the group generated by a to the k, if and only if k divides j. And you'll notice the reversal of the two integers k and j here on the two sides. And that should make sense, because smaller exponents should produce larger groups or subgroups. So that is the order relation in the subgroup lattice. Let's look now at the finite case. Suppose that G is generated by an element of order n. Then Lagrange's theorem tells us that each subgroup of G has order d dividing n. And so it is generated by an element of order d. Remember that every subgroup is cyclic. If it has order d, it must be generated by an element of order d. So we ask the question, exactly which elements, a to the k and g, have order d? Well, we already know how to answer that question. According to a theorem back in chapter 2, if k is in this range 0 to n minus 1, which is fine, then the order of a to the k equals d if and only if k is r times n over d, where r is in the range from 0 to d minus 1, and r is relatively prime to to d. So it follows that there are precisely phi of d elements of order d. And these elements belong to this subgroup of order d. And so this subgroup, the one generated by a to the n over d, is the only subgroup of order d in the group, because it contains all the elements of order d, so there are no other generators to generate other subgroups of order d. Then in summary, there is a unique subgroup of order d dividing n, and it contains all the elements of order d. As to the order relation, suppose that A and B are subgroups of our cyclic group G. If A is a subgroup of B, then Lagrange's theorem implies that the order of A divides the order of B. But the converse is also true, and it's a little bit trickier. Suppose the order of A divides the order of B. Then to see that A is a subgroup of B, note first that, of course, G is cyclic by definition, but B, being a subgroup of G, is also cyclic. So these two groups, B and G, have a unique subgroup of order the same as the order of A. But we know that A is the unique subgroup of G that has that order, has the order equal to the order of A, obviously. And so if, let's say, S is the unique subgroup of B that has order equal to the order of A, then since S is a subgroup of B, which is a subgroup of G, we know that S is a subgroup of G. Well, then, since it has order equal to the order of A, it has to be A. S has to equal A, because there's only one such subgroup. And so S, a subgroup of B, is the same thing as saying A is a subgroup of B. So A is a subgroup of B if and only if the order of A divides the order of B. Now, if we write generators for each of these subgroups, so let's say A is generated by A to the J, B generated by A to the K, then this subgroup is contained in this subgroup if and only if the order of A to the J divides the order of A to the K. That's precisely what this says. Now, we have a formula for the order of a power of an element. And if you should hopefully know that formula. If not, you can look it up. And then this, when you apply the formula, this is equivalent to greatest common divisor of K and N divides greatest common divisor of J and N. Now here's the reversal to, again, J and K. And this is the analog. Let me slide this down, of this formula. Here you just have K divides J. Here you have the greatest common divisor of K and N divides greatest common divisor of J and N. So there's an analogy, there's an analog there between the two cases. Actually, we can squeeze out a couple of bonuses from this, either of these, in the finite case. First of all, this sum over D, over all the divisors of N of phi of D, this is the number of elements in our group G of order D. All orders divide N, so this actually counts all of the elements of the group. It counts them by their order. So this sum is equal to N. This is a famous formula involving Euler's phi function, first proved by Gauss in 1798, which is before the development, really, of group theory. But we can get even more out of this. Suppose that G is an arbitrary group, not necessarily cyclic. It has order N. And we know that it has the property that G has at most one subgroup of each order dividing N. This may sound kind of strange, but it does come up once in a while. I think it will come up later on in this course. What can we say then? G has at most one subgroup of each order dividing N, the order of the group. Well, suppose that D does divide N. And suppose that G does contain an element A of order D. It may not, but we'll suppose it does. Then the subgroup generated by that element is the only subgroup of G of order D, because we're assuming there's at most one. So it must contain all the elements of order D. And therefore, G has exactly phi of D elements of order D. So if G has an element of order D, then it has exactly phi of D elements of order D. Now, at the moment, we don't know for which divisors of N the group has an element of that order. So let's suppose that these, D1 through Dm, are the divisors of N for which G does have an element of these orders. Now we take the sum over these divisors. So sum I from 1 to n, phi of di. Well, now this must count the total number of elements in the group. Because, again, we're counting the elements by their order. And these are the only orders. So this sum is equal to n, but we have established this fact. Once this is established, we did it using cyclic groups, but now it doesn't matter. We don't need groups anymore. This is simply an arithmetical formula. So n is equal to this value. But each of the terms in these sums is positive. So the two sums will not be equal unless the sum on the left includes all of the divisors of n. Otherwise, you'll be missing a positive term over here that exists on this side. So in particular then, because n divides itself, G must contain at least one, and in fact, phi of n, elements of order n. And that makes it cyclic, because it has an element of order equal to the order of the group. So, what we have established is that a finite group G of order n that has at most one subgroup of each order dividing n must in fact be cyclic. And therefore it has exactly one subgroup of every order d dividing n. So here is the theorem that summarizes all of this. We have a cyclic group. Every subgroup is cyclic. If the group is infinite, then each power of the generator generates a distinct subgroup. And this is the order relation in the subgroup lattice. If the order of A is n, then for each d that divides n, the group has exactly one subgroup of order d and exactly phi of d elements of order d, all of which lie in that subgroup. And that accounts for all the subgroups of the cyclic group. And we also have this relation. This tells us that the subgroup generated by a to the j is contained in the subgroup generated by a to the k if and only if the order of the former divides the order of the latter, or if and only if this relation holds. And this is Gauss's theorem from 1798. Right? 1798? Yes. Okay. And the second part of this theorem, if G is a finite group of order n, and if it has the property that it has at most one subgroup of every possible order, in other words, of every d dividing n, then G has to be cyclic. Look at an example. Let's say G is the cyclic group of order 24. And we want to examine the subgroup lattice. So we know that for each divisor d of 24, there's a unique subgroup, C sub d, of order d. These are the positive divisors of 24. This is partially ordered by divisibility. This stuff up here tells us that the subgroup C sub D1 is contained in C sub D2 if and only if D1 divides D2. D1 being the order of this one, and D2 being the order of that one. Now, there's a more sophisticated way to look at this, and that is we define a map, sigma, from the divisors of 24 to the subgroup lattice, and we send a divisor to the corresponding subgroup of that order. Here's the picture. This map is an order isomorphism. That's what this tells us. And here's a picture of sigma. This is the lattice of positive divisors of 24 under divisibility. The exact same picture, the same Hasse diagram for the subgroup lattice of C24. Corresponding to each of these divisors of 24 is a subgroup of that order. So one could say that this side here is more complex, perhaps because we're dealing with subgroups of a group. You need to know something about group theory. This side is just a bunch of positive integers under divisibility. And the fact that these are isomorphic means that you can represent the subgroup lattice by what is arguably a simpler lattice. It's an isomorphic lattice, but it's simpler in the sense that the elements are just positive integers and the relation is divisibility, which I guess is known even to perhaps elementary school students. And one can generalize this example. For a finite cyclic group Cn, the subgroup lattice is order isomorphic to the lattice Vn of positive divisors of n, again under divisibility. One more example. For infinite cyclic groups, let's say a group generated by A, there is a similar situation, but definitely different. Recall from our discussion that in the case that A has infinite order, that this subgroup is contained in this one if and only if K divides J. So we can define a map, sigma, from the positive integers to the subgroup lattice by sending K to the subgroup generated by A to the K. And this is easily seen to be a bijection, but it does not preserve order like the map in the finite case. It reverses order because of the flip, the exchange of K and J. So what this tells us in terms of the map is that K divides J if and only if sigma of J is contained in, or is a subgroup of, sigma of K. A map like this, a bijection that reverses order, is called an order anti-isomorphism. So in the infinite case, we can say that the subgroup lattice of an infinite cyclic group is order anti-isomorphic to the positive integers under divisibility. There is one more matter related to finite cyclic groups that will prove useful to us later, so we'll discuss that now. And this is the matter of how finite cyclic groups might be combined to form larger cyclic groups, and in the opposite direction to be decomposed into a direct product of smaller cyclic groups. So combine and uncombine, you might say. Let's begin by considering a direct product of finite groups. So G is the direct product, we're talking external now, of G1 through Gm. If each group G sub I is cyclic, then we can write this equation in this form, where the A sub i's are the generators of the cyclic groups. And the question is, does that imply that G has to be cyclic? Well, the answer to this question is no, and all you have to do is look at the Klein 4 group, which is the direct product of two cyclic groups of order 2, but the Klein 4 group itself is not cyclic. It does not have an element of order 4. So the next step is to find conditions that will tell us precisely when a direct product of finite cyclic groups is cyclic. We know, of course, that a finite group is cyclic if and only if it has an element whose order is equal to the order of the group. That would be the generator then for the cyclic group. So we should examine the orders of the elements of this group G. To determine the order of an arbitrary element, written here, we observe the following. Say b to the n, take the nth power of b, would be equal to 1. That would look like this, if and only if each of these components is equal to 1. And so that would be equivalent to saying that the order of each component, b sub I in B, divides n. Because we want n to be an exponent of b sub I. Well then, that tells us that the order of B is going to be the smallest n for which this divisibility relation holds. N here is a multiple of the order of bi, so the order of B is the least common multiple of the orders of the components in our element B. Now, G is cyclic if and only if it does have an element, which again I'll call B, of order equal to the order of the group. And that would mean that B satisfied this property here, that the least common multiple of the orders of its components would equal the order of the group, which is the product of the orders of the generators here. Now, I'm going to leave it as an exercise to show that this will hold if and only if the order of each b sub I is equal to the order of the corresponding a sub I, and the orders of the a sub i's are pairwise relatively prime. Well, the first condition is easily fixed because B was an arbitrary element, so we'll just take Bi to be equal to the generator Ai for all I. That takes care of that. So we can conclude that G is cyclic if and only if the orders of the generators of each factor here are pairwise relatively prime. So what we've shown is that a direct product of finite cyclic groups is cyclic if and only if the orders of the factors in the direct product are pairwise relatively prime. Now, we're not done with the analysis yet. We want to go in the opposite direction. Suppose again we have a direct product decomposition of G And suppose this time, not that the factors are cyclic, but that G is cyclic. What can we learn about the factors, G1 through Gm? Does it follow that they have to be cyclic? Well, it's kind of tempting here to say, yes, they must be, because they look a little bit like subgroups of G. And we know that if G is cyclic, all its subgroups are cyclic. But Gi is not a subgroup of G, but it's almost a subgroup. And what I mean by that is that if you fix a particular index I, this group, which is a direct product where you've replaced all the other G sub i's, I should say G sub j's, by the trivial group, and I'm going to write this as G superscript I in parentheses. This, and here G sub I is in the ith position, these are subgroups of G. And so they are cyclic. And so, for example, we can write G superscript I this way, the group generated by the generator of this group is going to have all ones except in the ith position where it has the generator for G sub I, in fact. And so there's a couple of ways you can think of this. You can easily find an isomorphism between this group and G sub I. So if this is cyclic, so is G sub I. But more directly, if we take an element from G sub I and we stick it in this ith position here with ones everywhere else, then this belongs to G superscript I, and so it's a power of the generator, and this K comes inside, looks like this, and so X is AI to the K. In other words, the elements of G sub I are all powers of A sub I, and so G sub I is cyclic. Once we have determined that the G sub i's are cyclic, then we can appeal to what we did previously to say that the orders of these groups actually have to be relatively prime, pairwise relatively prime. So, in summary, a direct product such as this, where G has finite order, is cyclic if and only if each of the factors G sub I is cyclic and the orders of the factors are pairwise relatively prime. And that will prove to be a very useful result. It's a very powerful result. For example, it tells us immediately that this group is cyclic because we have order 2, order 9, order 13, order 35. They are pairwise relatively prime. And so this group is cyclic, and its order is the product of the orders of the group, so it's 8,190. But this group is not cyclic because 2 and 14 are not relatively prime. So it's a very nice theorem. This makes for excellent test questions. You put a question like this on a test: is this group is this group cyclic or not? Is this group cyclic or not? And the answer, of course, is easy. It's short if the person who's taking the test knows the theorem we just went over. Now let's suppose that G is cyclic and that we take its order D and we write it, we take its prime decomposition. So the factors here are pairwise relatively prime. Then for each index I, this element, a to the d divided by di, has order di. But these integers are relatively prime. They're not pairwise relatively prime, but they are relatively prime. And so Bezo's identity tells us that there are integers k1 through kn for which this holds. So whenever we have an equation like this, it's always tempting to use both sides as an exponent. So A, which is the generator of the group, is equal to a to the 1, which is equal to a to this mess here, which can be written this way. And this element clearly belongs to the set product of these cyclic subgroups, because they are powers of this generator here. So the group we started with is in fact a set product of cyclic subgroups. So a decomposition of the order of the cyclic group G into pairwise relatively prime factors produces a decomposition of the group itself into a set product of cyclic groups whose orders are relatively prime. I'm sorry, pairwise relatively prime, I should have said. We can also show that this cyclic group is isomorphic to a direct product of these groups involved in the set product. It's not optimal here. It would be better to show that this cyclic group is actually an internal direct product of these subgroups, which is true, but we haven't defined internal direct products at this time, so I can't do that. But it turns out that internal and external direct products are isomorphic, so it's almost as good as what I'd like to be able to do. Just as an aside, there's always a problem in organizing any course in advanced mathematics because the mathematics is not quite linear, and so it's hard to organize or arrange the topics so that you never have to look ahead. In this situation, I'd like to be able to look ahead and borrow the subject of internal direct products so I could talk about them here, but that's not very feasible, really. So these are problems that we face in trying to design a course. There's the dependencies of the various topics are quite complex, and one can't always organize everything exactly the way one would like to. So to show that this cyclic group is isomorphic to this direct product, this external direct product, we can define a map, sigma, that sends this group, the cyclic group, to this direct product. And I'm going to set sigma of the generator to be this ordered n-tuple. Now that doesn't automatically make this a group homomorphism. Then this would tell us how to apply sigma to any power of A, if this was a homomorphism. But we discussed this matter of defining homomorphisms on cyclic groups to some other group, and that was back in Theorem 242. And that tells us that this does in fact define a group homomorphism because the order of each of these divides d sub I. And so, see this, without the ki here, this element would have order di. So this is a power of an element that has order di, and therefore it divides di. And so the order of sigma of A, that's this element here, it's the order of this n-tuple, we know to be the least common multiple of the orders of the individual components, and that will divide the product, d1 through dn, which is the order of A. And that is the key that tells us that sigma, when we extend sigma from A to all powers of A, that will be a group homomorphism. So you might want to go back and look at this theorem. Okay. And this is a perfect use for that theorem. Okay. So we do have a group homomorphism. To see that it is injective, we can appeal to another theorem from Chapter 2, which says that the map is injective if, since it's a homomorphism, is injective if and only if its kernel is trivial. So, which elements are in the kernel? Well, sigma of A to the j is equal to 1. In other words, A to the j is in the kernel of sigma. If that's true, then this is sigma of A to the power j. Sigma is a homomorphism, so that j comes outside, is equal to the identity. And that now the j's can be distributed. We get this, and that means that when we compare coordinates, that this equation must hold for all I, and that tells us that d sub I divides j ki for all I. Now we multiply this equation by j, as we're trying to show j is equal to 0. So we want an expression for j, and since this is equal to 1, if we multiply both sides by j, we get j equals this expression, pull out the d, put in the j, and now we have an issue, and that is j is less than d. But here it's expressed as d times something, okay, times some integer. So the only way that can happen is if j is 0 and all of this stuff is 0. And so j is 0, and therefore a to the j is 1. That shows that the kernel of sigma is trivial, and so sigma is injective. But also, the orders of the domain and the codomain are the same and finite. And so injectivity implies surjectivity, and therefore sigma is an isomorphism. So in summary then, if G is a cyclic group generated by A, and if we decompose the order of D, the order of A, this way is D, call it D, and we factor it into pairwise relatively prime factors, then the cyclic group is the set product of these cyclic subgroups, which is isomorphic to the external direct product of the same subgroups. and this will also prove useful to us.